Welcome back. We are continuing on ray tracing in one weekend in Rust. This is the image we're building up to, but I'm actually going to stop for one video from going through the book chapter by chapter and focus a little bit on optimization and profiling. I was thinking about the code I have so far. This is kind of my main render method, and I've made a few changes off camera just so that this video won't be too long. But the core of it is the same, which is that we're iterating here, this double for loop. We're iterating through all the pixels in the image, sending out a handful of rays for each one to determine what color each pixel should be, and then writing that out to our ppm file. But this is totally sequential. There's no opportunity, the way this is written, for the program to run in parallel at all. And if you're on a multi-core machine, which most machines are now, you're really not taking advantage of all the cores that you have. So I thought I would try to parallelize this main loop a little bit, but then I thought that probably before jumping into that, it'd be good to do some profiling. So I checked out this project called Cargo Flame Graph, or I guess called Flame Graph, but there's a way you can use it with Cargo, and it'll produce an image like this. The way to read this is that each horizontal bar that has the name of a function on it, the bigger the bar is, the more time your program is spending in that function. And then if that function calls into other functions, those show up as smaller bars on top of it. So this h269 function calls this other function, hb7b, which then calls this path4 key h27 function, and so on, and gives you a sense of where your program is spending the most time so that you can decide where to optimize it. So the first thing I did is just write a little script that calls cargo flamegraph that produces this flamegraph.svg file. So we just open it up. And first let's just call our ray tracer like normal. Ignore that compiler warning. It is a valid warning, but it's a field that's unused now and we're going to use it later. But anyway, so we're still producing this same gray sphere on top of a bigger gray sphere. But now let's run our flamegraph script. Oh, yeah, you have to set this. Where is it? Yeah, here we go. I think I did set this before and it just doesn't persist between reboots. Okay, great. So it's collecting all this data, writes out this file, and what might surprise you, we're doing all this vector math to calculate the colors, but you can see a huge chunk of time in this part of the flame graph, and this part is just the actual file writing. Previously I was writing to standard out. One of the things I changed off camera is that now we're actually writing to a file. But the flame graph was pretty similar. The actual just file I/O or output to standard out was taking up a decent chunk of time. And that kind of makes sense in a way, right? Because here in self.writeColor, this is where we're doing the actual writing. We're only writing, these are usually 3-digit numbers, so we're writing like 12 or 13 bytes or so. And then going back and doing more calculation and then writing another 12 bytes and so on. So it's probably going to be more efficient if we buffer those outputs and then write a bigger chunk of data all at once so that we're not doing a ton of tiny little writes to the file system. And of course Rust has a nice built-in struct to do that called a buff writer. So we'll say let output equal buff writer new. And then we'll pass that to the camera, this buffered writer, instead of just the raw file. And if we look here, it says that it is critical to call flush. Whoops. It is critical to call flush before buffer is dropped. All right, so let's just do that. And now it says borrow of moved value, value borrowed here after move. Okay, so instead of letting the camera take ownership of the output, we can just pass it a mutable reference to the output. And then it says we can't borrow it as mutable, so we just got to make this mute. And output.flush returns a result, so let's just do question mark. And again, let's first just run our ray tracer, make sure everything still looks good. And then run our flame graph. Let's make sure to close this so that we're looking at the new version. And now you can see most of the time is spent in the ray color function, which is, you know, the actual like interesting vector math. What's weird is there's a bunch of function calls over here that look like they're not being called as part of main. Here's our main function. I assume that's just some kind of bug in the flame graph infrastructure, because these, you know, random number functions and things definitely are being called from main, but here it says unknown, so for some reason it failed to capture the function names for part of the stack, I guess. But anyway, the file I/O is almost completely gone. I can't really see it anywhere, to be honest. So I think that tells you we sped things up quite a bit just by buffering the writes. So that's great. And now let's go look at that main loop that I was talking about. So the way that I've usually seen people say to parallelize something like this in Rust is to use a crate called rayon, which is appropriate because we're doing ray tracing. And this is a pretty interesting crate. I ended up spending a decent amount of time kind of reading through the docs, but this page is really the only core thing you need to know to get started. Typically, all you have to do is convert the first iter, or iter mute, etc., into par iter, or par iter mute, etc. And they give an example here where we're taking in a slice, and instead of calling map, or instead of calling iter and then map, you call par iter and then map. And so it's able to do this squaring in parallel. So it's pretty cool. You don't have to think a lot about threads and thread pools and how many threads should I have. All right, so I'll go ahead and add that in and cargo add rayon. But it's not trivial. Oops, I lost my render method. It's not trivial to add that because we're not calling iter here. We have these two for loops instead. So I guess the first thing we probably want to do, I'll go ahead and take out this logging. I don't care so much about that. The first thing we want to do is, instead of generating our little ij pairs for the pixels with this nested for loop, we will create an iterator that does that. So we'll use this same range. A range is, I can't remember if it is an iterator or it can be turned into an iterator. I think it actually is an iterator. And we can call flat map here. There we go. So flat map takes the trait. Ooh, this is an interesting error. The trait iterator is not implemented for exclamation point, and the exclamation point is the never type. Oh, the never is the return type from the to-do. Sure, that's fine. But I just wanted to look at the type of flat map because it helps you think about how you're supposed to do it. So the argument is f, a function, which takes a self.item. In this case, that will be the j's from this first iteration, and it returns a u. And then the flat map overall will return also a u. Okay, so basically we want to, in this closure, then do sort of the inner for loop, the I for loop. So 0 to self.imageWidth. And then for each I, we just want to take it and pair it up with the j that it got. All right, first error is here. It says to force the closure to take ownership of j, use the move keyword. Okay, I will do that. And now this whole thing returns an iterator that must be used. So let's call that pixel chords. And then here, instead of our double for loop, we can just say pixel chords dot for each ij, do all of this. All right, now this is a little tricky because self.writeColor is where we do the actual file write, and that returns a result because it could fail if the file system rejects our write for whatever reason. So I think what I'm going to do instead is take this. This is another thing I did off camera, by the way. I just took the color here, which is a vec3, it's 3 floats, or F64s I should say, and converted that to the ppm color, to what we're going to write, which is just a triple of U8s, and triple of bytes. But anyway, I think what I'm going to do is actually return this to ppm color, and then do the write at outside of the loop. So that means this is going to be map, because we're not just running this code for each pixel, but actually running it and getting a return value and then storing those in another iterator. So let's call this pixel colors. And then here we can just say for pixel color in pixel colors, write it to the file. Or I'll call it ppm color. Yeah, because pixel color here is actually a vec3, so I'll use ppm color just to be a little bit clearer about the two different types. All right, cannot borrow self as mutable because it's also borrowed as immutable. So this is an interesting error. So pixel chords actually borrows self because it uses self.imageHeight and self.imageWidth. And ppm colors is based on pixel chords because it's built by calling map on pixel chords. And so when we're iterating here, we still have self borrowed as an immutable borrow, and so then it's saying we can't then borrow it again here. So the easiest way to fix that I've been able to find is to just go ahead and collect this into a vec here. So now this vector only contains the actual pixel data, just the bytes that we're going to write. It doesn't contain any references back or borrows of self, of the camera object. All right, so we haven't done anything parallel yet. We've just converted our code to use iterators a lot more. So it shouldn't be any faster, but it should still produce the same image, and it does. Actually, before I go into this, I want to make the image a little bigger to make it slower on purpose so that if there is a speed up, it'll be a little more obvious. Great. And it took about 5.5 seconds to render that. So now the Rayon docs told us the first time you call iter, you should instead call ParIter. So when I tried this the first time, I did it this way, and it said, well, this is sort of a confusing message. The method ParIter exists, but its trait bounds were not satisfied. So it's saying this iterator pixel coords does not implement the necessary trait to call ParIter. And I thought, okay, that's weird, but I thought it was supposed to work for pretty much any iterator you can think of, but I guess not. Okay, so I guess I'll just collect it into a vec, kind of like I did down here for the colors at the end. And then here I would just call iter.map if I was doing a normal sequential operator, but instead I'll do ParIter. And that should work. And then it says arguments are incorrect. If we mouse over the I and J, I think it will tell us why. Expected I32 found reference to I32. All right, well, then we can just dereference those. Nope. Well, let's see. If these are references, we really only need to go through this loop once. We only need all the pixels because we're trying to calculate a color for each pixel. So what we could do is instead of calling iter, call into iter and actually consume the vec. Or in this case, into ParIter and consume it. And now we have a different error. Let's see. It says f cannot be shared between threads safely. Required because it appears within the type camera f. Consider further restricting type parameter f with trait sync. Well, generally, if the compiler asks you to consider something, it's a good idea to consider it, and that's exactly what we'll do here, is just say f, which is our file, or rather our buff writer wrapping the file. Oops, there we go. Just needs to be sync for this parallelism to work. And we have that referenced also. Oh, okay. Yeah, so that fixed that. And then we have the same error for a different trait. W, which is our world, in practice, this is generally a collection of spheres, also has to be sync. So we'll just add that here. And now this compiles. Remember, it took about 5.5 seconds before. And now it takes only about half a second. So something like a 10 times speed up. You can see here it's actually using a lot of CPU time, but because it's able to parallelize so well, it only takes a half second of real world time. So I actually did it this way and recorded the video, and I was about to upload it to YouTube, and I thought, wait a second, this really kind of sucks, right? Let's say we have an image that's 1,000 by 1,000. This is 1,000,000 pixels, and we go through this loop. This loop should be pretty fast. We should be able to start generating a few pixel coordinates to work with almost immediately, but we can't use any of them until we wait for them all to be generated so that we can collect all of them into a vec. And then we have this 1,000,000 element vector that's sitting in memory when there's really no reason to do that. We don't need to be keeping all of these coordinates in memory just so that we can calculate with them. And it took me a little while to realize what I did wrong here. Or not wrong, but that there's a much more straightforward way to do this. So if you go back to the Rayon docs here, it says, all you have to do is convert the first, that's the key there, is the word first, iter. Well, I thought this was the first, but it's really not. Really, the first thing that we're iterating is this, this range, which is iterable. So if I start there and say pariter, let me take this out because now we shouldn't actually need it. Well, now it says pariter exists for struct range, but its trait bounds were not satisfied. Well, let's see. Parallel iter types for ranges. Oh, so we have to call into pariter. Right, because the range itself is the iterator, so we're going to convert it. And then it says the trait bound map is not satisfied. So let's see. Let's go into the ParallelIterator trait. And it has a method called flatMap. What we got returned from into pariter is a parallel iterator. And flatMap here takes an f, where f is something that returns a PI. So it returns a parallel iterator. But here, this is just a regular iterator. And of course, we call map, we still just have a regular iterator. So I think there's a couple ways we can deal with this, but it says see also flatMap iter, which is right below. And flatMap iter, your function, your closure that you pass in, returns an SI, which is just a regular iterator, or at least something that can be turned into one. So let's try that first. Okay, and it looks like that worked. And now I kind of have the same complaint again here. We're collecting all our colors into a vec just so that we can write them out. But I think in this case that actually does kind of make sense, because this mapping, this kind of inner loop that's doing all the interesting vector math, it's not going to necessarily return all of its answers in the right order, and so we do need to sort of collect back into some kind of normal iterator, not a parallel iterator, in order to then write them out. But maybe there's a better option here. So collect here, this is actually not the standard collect method from Iterator, but the similar one from ParallelIterator. So let's go to that collect method. It says you may prefer collect into vec, okay, but that's still going to give us a vec. Or we have this collect vec list. Collects this iterator into a linked list of vectors. It says this is useful when you need to condense a parallel iterator into a collection, but have no specific requirements for what that collection should be. Well, I think that fits our case here. The only requirement we have is that it is something we can iterate over in this loop, and that it will iterate in the correct order. So let's try that. Let's try collect vec list. Oh, okay. So then this becomes actually a linked list of vec. Well, let's just say this then for, so let's call this vec list, and then we can say for ppm colors in ppm color vec list, run that. All right, I think that's reasonable, and it still runs in about half a second. So I just wanted to do this slight digression to speed things up. One, as an excuse to learn how to use the rayon trait, but two, to make the code a lot faster as I get into the later chapters of the book so that I'm not waiting and waiting for it to render. And I can kind of get into, keep the flow going as I'm getting into the last few chapters about different types of materials and angles of refraction and all that fun stuff. So again, hope you're enjoying the series. I'll try to get the last few videos out in the next week or so. I do realize it's called ray tracing in one weekend, and I've gone well past that, but I'm having fun. I'm learning a lot. I think it's worth it. See ya in the next video.